they are statistically independent, then the probability density function is the product of the probability density function for each value. And so the joint of PDF is the product of the individual one, okay? The margin, if you like. And so the likelihood function, or the log likelihood, is, you remember, the logarithmic of the product becomes the sum of the logarithm, okay? And so that is the sum of the logarithmic of that one and the sum of individual log likelihood. So some special cases. Now, some as a curiosity, if you like, assume that I have a noise that is uniform between plus and minus A. Now, if the noise is uniform between plus and minus A, and that means that the probability density function is 1 over 2A in when W is between plus and minus A, then the maximum likelihood is is calculated by finding what is the parameter theta that is making this error to be maximum constraint that is lower than A. So I'm looking for for each of that such that is the maximum one, and this has to be lower than A. So the error. Another more interesting, much more interesting, is when noise is Laplacian. Now, noise Laplacian, is very important, because noise Laplacian is when the probability density function has a tail that are bigger than a Gaussian. Now, let me spend a word on that, because Laplacian is kind of important. Now, what does it mean, Laplacian and Gaussian? If I look at the Gaussian PW, is equal to blah blah blah, and then it's exponential, or minus W squared divided by 2 times C squared. Okay? But when I look at this is Gaussian. Now PW as a Laplacian is exponential of minus W divided by sigma squared. This is Laplace. Now, what is the major difference? The major difference is that, in a distribution, in a probability density, this is W, and these are the distribution. So the Gaussian, is behaving approximately in this way. So it's a bell shape. Okay? So this is the Gaussian. What about the Laplace? Now the Laplace, is characterized by having larger tail. What does it mean, larger tails? It means that, in the Laplace distribution, I might have bigger amplitude, bigger than the Gaussian. So, it's peculiar in this way, in this sense, okay? Because, the Laplace has a bigger tail. So it's a noise behavior that, in some cases I can find it, and, if I manipulate my data as if they are Gaussian, I make a big mistake. Because I'm not accounting, I'm not describing properly the tail. The tail is, it's larger. So, I'm trying to sketch it, okay? So, Gaussian, it's this way, okay? But, the Laplace is more spiky. So, I have some behavior, then pump, okay? So, what we have been doing is modeling or manipulating the behavior as if it is Gaussian. And what we get is that our optimization function for a maximum likelihood is a quadratic form or similar. Okay. Now, what about for a plus? Now, let's see. So, if I make it for the Laplace, okay, so what I need to do is I need to write the log likelihood And so when I need to find the maximum likelihood is given by the sum of the absolute square, which is different from the sum of the square. So the new metric is the sum of the L1 norm, which is different from the L2 norm. L2 norm, is the sum of the square. It's the sum of the square of the error. Here is the error, depending on theta, on the sample n, but it's the sum of the absolute value of the error. If Gaussian, just to call, if Gaussian, it would be the sum of epsilon and theta squared. Okay? Just to recall you. So the Laplace, is summing the absolute value. The Gaussian is summing the square. So what does it mean? It means that, if it is Laplace, the larger error are not counted with the square, because if it is the sum of the square of the error, the square, that means that every error is taken to the square. So big error are weighted much more than the small error. In a Laplace, what's happened is that it's linearly weighting. So because it's the metric is linear, so in the error. So if I take, this one is the error epsilon n. So in the Laplace, I am measuring the absolute value of the distance in the Laplace. As a Gaussian, that will be this way. So this is, this is the remark that I do it on the Laplace model. Now, the noise with the big tails exists, and for this reason, in some setting, we need to design estimators that are able to manipulate the case where these big tails are entering into the estimation process. And this class of estimators that are manipulating the data when the data contains larger tails are called robust estimators. So robust estimators are this class of estimators that are taking into account the presence of larger tails. And we will see in a minute about that. Now, in a general class, this is the most general. Now, the general case of exponential distribution is when the probability density function of the noise is exponential minus a certain function. And the maximum likelihood, for this case, when independent samples is given by the sum of these functions. And you see that if the function itself is quadratic, which means as a Gaussian, then we have the L2 norm. If it is the absolute value, then we have the L1 norm as for the Laplace. So this is the most general one. When we might have different cases, we are not considering this course. Now, this is a kind of delicate problem. The problem of nuisance. Now, what is a nuisance parameter? A nuisance parameter, is a set of parameters that, is part of the estimation process, but is not really of interest for my application. Now, let's assume that my goal is to estimate the frequency of the sinusoid. But in modeling the sinusoid, there is a frequency, amplitude, and phase. So my interest is only frequency, and also what about amplitude and phase? So if the interest is frequency, I need to, in some way, estimate amplitude and phase. Amplitude and phase are part of the model, but they're not of interest for me because my goal is to get the frequency. So that amplitude and phase are called the nuisance parameters because they are parameters that are representing the model, but it's not parameter of interest for my application, for my case. Now, how to handle nuisance? Now, there are two ways. The simple way is that, I estimate the nuisance as well. Okay, so, remember, amplitude, phase, and frequency. Just to keep in mind, because we will make it. So, sinusoid, xn. Let's make it complex. Okay, so I have A, and then I have AJ omega n plus P. Okay. So my goal, so my parameter is omega. Okay, so this is of interest. Now this amplitude and phase are nuisance. My goal is to get the frequency. Okay, so this is the parameter of interest. Now, how do I handle this problem? I handle this way. Option number one, my theta is equal to omega, amplitude, and phase. That's it. So I handle the nuisance as parameter. Perfect. Okay, and then I keep moving. Okay, so that means that at the end of the story I get the amplitude and phase, but I'm interested in frequency. And then I get the frequency. Now, it is not that strange. Because remember, when I was estimating the frequency, I came out to have a projector, and the projector was dependent on frequency only. So in that case, I remove the dependency on amplitude and phase. Well, let me go back. So I make it more concrete. Yeah. Okay. So how did I do it? I did it this way. I have the frequency and omega, alpha. Alpha includes amplitude and phase. Okay? So then my goal is to estimate the frequency and frequency only. But there is amplitude and phase there. Okay, so what I do is my set of parameters is amplitude and phase and frequency. Then what I did is I estimate, I isolate the parameter that was easy to estimate, and then in the minimization process, and then that is the amplitude. Then I found the amplitude. I plug the amplitude there, then I come out to the function of the frequency. Here it is. This depends on frequency only. So what I did, I removed the dependency on amplitude and phase. And then I kept moving. And then I found these, okay, that one, this is more general, this is specific, okay, which is the way to estimate the frequency. So in this case, I managed to remove the dependency on amplitude and phase, which is apparent, but that means that amplitude and phase are nuisance. I estimate amplitude and phase. Okay? Now, we will see the impact of nuisance parameter into the Kramer out later. But right now, up to now, the nuisance parameter goes into the budget of the estimated parameters. We need to estimate that. Let's see a new method. The new method is that I know about the nuisance parameter some statistical properties. For instance, I know some probability density function about of the nuisance parameter. So what I can do is I can marginalize with respect to the nuisance parameter. Now, so what does it mean? Assume that, like in this case, this is the general, the most abstract way. So I have a set of parameters. So theta 1 are of interest and theta 2 are nuisance. Okay, so I group the parameter into those that are interested and those that are nuisance. Now, let's assume that I know something about the nuisance parameter. For instance, I know about the nuisance parameter, the distribution of the nuisance parameter. Now, let's go here. Let's make it this way. Nuisance parameter are the phase. Phase is nuisance. Okay, what can I say about phase? Now, what is the phase of the sinusoid? Phase of the sinusoid reflects the asynchronicity of a sampling, of a segmenting the data. Which means this sinusoid is going this way. Then I take this interval. Okay, so this interval is the interval of the n samples. Now, this is the amplitude, and the period is setting the frequency. But the phase, this is depending on the phase. The phase depends on where I window my data. So if I choose the window here, or I choose there, the phase changes. Am I interested about the phase? No. The phase is part of the experiment. So I'm not really crucial, the phase is not really crucial in my experiment. This only happens to be that because of how or where I segmented the data. So phase is nuisance in this case. Now, how can I model statistically the phase? Well, since this window might be everywhere, I can say that a phase is uniform between -5 and 5. That's an assumption. I don't know what is that. So, uniform distribution means I know nothing. When you say my distribution about a parameter is uniform, means it can be everything within the interval. It's not the one value that is more privileged than the other. It's uniform. Okay? So when it's uniform, remember is the maximum ignorance, because it goes anywhere within that interval. So this is exactly that. So when I'm talking about this distribution, about the nuisance, think about that. Now, what I'm saying is, since I can write the Laplace function. Okay, so once I have px, depending on this set of parameters, I can either maximize with respect to theta 1 and theta 2, which means treating the nuisance as a parameter, as before. Okay, and the other is the following, this way. This is the same. Let me write it as conventional. Treating theta 2 as a parameter. Okay, and the other is, let's consider that now in my distribution I know that some a priori information about the distribution. So let's consider the nuisance is modeled as a random variable with some a priori distribution. Now, that means that I can calculate now the probability density function marginalized with respect to the theta 1, which means I have a dependency on theta 2 and theta 1 when I multiply by theta 2 and then I integrate. Okay, when I multiply by the probability theta 2, then what I get is p x theta 2 depending on theta 1. When I integrate now with respect to theta 2, then I'm marginalizing. Okay? marginalizing, I'm taking out, I'm averaging all the possible state of theta 2. I'm computing, and it's saying computing the expectation with respect to theta 2 of all these possible options about, the value of the nuisance. Now the good news is that this new function is the probability of x1 depending on the condition to theta 1, so depending on the parameter theta 1. So nuisance has been removed. So I'm averaging out all the possible state of the nuisance in this way. Now, in some cases, these expectations, so basically, all this is carried out by the marginalization with respect to the nuisance. So, in some cases, these expectations with respect to the nuisance parameter might be easy, in other cases, it might be complicated. Now, but out of any question, if it is possible, you can do it, you can make it. Let's look at an example, and specifically that one. So let's consider, for instance, that example there. So, I have a set of observation, amplitude, frequency, and phase, and then plus noise. So, since this one is complex value, so I can write the Gaussian for complex variable. Okay, let's do it. And this depends on amplitude, frequency, and phase. But now, phase is a nuisance. And so, what I can do is, I can average with respect to the nuisance parameter. So, this means specifically that I can calculate this marginalization. So, the marginalization here is the expectation with respect to phase phi of the probability of x a omega phi. I'm removing the dependency on the phase. Now, that means that I take this big function, I move into there, I compute it, blah, 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 that it's not necessary that you learn by memory to do it. And it comes out a function where I will remove the dependency on phi, because I integrated with respect to phi. So, the function that depends on data, amplitude, which is not known, okay? And here, this x omega is the Fourier transform of the data. I0 is the Bessel function, one of the Bessel functions. Okay, so that means that in this stage, this one does not depend on phase. And so my goal is that I need to maximize this one, this function. This is the Laclue function. So now this specific is a Laclue function. That is a Laclue function that depends on amplitude and omega, but not on phase. So I maximize that. Is it easy? Well, if you think about that, the life is just a plus b equals c, so a very easy trivial function, trivial equation. Better to forget it. So it's complicated, but once you put in MATLAB, it's easy, because you need to put in MATLAB computational Fourier transform. Okay, you do it. Bessel function, you get it. Okay, then it can be done. Now let's look at a little bit. Let's gain some insight about that. So the Bessel function, when the argument is very big, the Bessel function is approximated as an exponential. Then it's a scale by the square root of x. So I can take this one, and then I can use this approximation. We remember that this approximation is only when the argument is very big, which means this one is very big. What does it mean? This one very big means that 2a Fourier transform divided by sigma w, which is noise, very big. Okay. So we will see that these absolute value of the Fourier transform is called, will be called the periodogram, but that's something that we will see. So, now, what is the maximum likelihood now? The maximum likelihood is simply the maximization of that new likelihood function, okay? Which, just to copy, it's A and omega. It's just being obtained by marginalization. Now, we can say that since this is the power of the data, and this is the power of observation, but this is the Fourier transform. So since the Bessel function is monotonic, so it's always increasing, okay, with respect to the argument, we can say that the maximization with respect to omega is just the maximization of the absolute value of the Fourier transform. So we know that we got the specific solution. That if you want to estimate the frequency of the sinusoid, is just finding the argument that is maximizing the Fourier transform of the data. Now, which means I get the data, I make the Fourier transform of x. By the Fourier transform, this is omega. The Fourier transform is behaving this way, okay? So that means that the estimated value is the argument which is maximizing the Fourier transform. Okay, that's hat. This is omega. Okay? It's not complicated, right? Okay. So at the end of the story, the maximum, the frequency that maximizes the Fourier transform of the data is the estimator of the frequency of the sinusoid. But we are strong because we can say that the phase contribution is being neglected. Now, if you want to get the amplitude, well, the amplitude is a little bit more complicated. So that means that we need to take this value, which is I call x star, the value of the Fourier transform at the maximum is x star. Okay. Then I take this, which is the maximum, plug in here, and and I use the approximation. So when I use the approximation, blah blah blah, it comes out that the maximum value, is a certain formula which can be approximated, which I can approximate. Here it is. So the extreme approximation is that this amplitude is a scaled version. This amplitude of the Fourier transform is a scaled version of the amplitude of the sinusoid. So what we got is that the amplitude of a sinusoid is a scaled version for that. So when I make a Fourier transform, I look at the maximum. The position of the maximum gets me the frequency. And the amplitude of the Fourier transform divided by n gives me the amplitude of the sinusoid. So at the end of the story, practically, let me say, the practical procedure is kind of easy. But we need to prove the correctness of the overall procedure when you do on the real data. Because if you routinely do it, I take the Fourier transform and I pick at the maximum. If someone asks you, are you sure you're doing the best? Can you do better? Now, if you don't know the answer about that, means that you are losing. You're losing the job. You're losing the consultant opportunity. Because if you don't know if your procedure is optimal or not, if you don't know how optimum is your procedure, that means that, you know, you are not controlling your algorithm, you are not controlling the method you are proposing. It's like you know, you ask a plumber. If you ask a plumber, the plumber is fixing your, water leakage, and you ask the plumber, are you sure that in 1 month it's not leaking anymore? And if the plumber says, I don't know, then you say, I'm not paying you, right? Okay. It's 11 again. Okay, we continue on that tomorrow. Continue on that.